So an amusement park ride consists of a cylindrical room, a radius 5 meters, in which people stand with their backs up against the wall. It begins rotating faster and faster, causing the riders to stick to the wall. And when it reaches a rotation frequency of 1 over pi revolutions per second, it maintains that rate of rotation, and the floor slowly drops away. And the coefficient of static friction between the riders and the wall is 0.6, and the woman on the right side in the figure has a mass of 70 kilograms. So we're going to start with the free body diagram for the woman, and she has the downward gravitational force. She has no floor beneath her, so she has no upward pointing normal force, but she has the wall that she's stuck to, which is a vertical surface, so that has a normal force pointing inward toward the center of the rotating room. And then it's friction that is preventing her from sliding down the wall. So the friction is pointing up the wall, and that's static friction because she is not moving relative to the wall. And if you want to add on the centripetal acceleration arrow also, that is pointing toward the center of the circle. So part B, state which force on the free body diagram provides the centripetal acceleration and calculate the magnitude of that force. Well, the one that provides the centripetal acceleration is whichever force is pointing in that direction, which in this case is the normal force. So the normal force is what we're going to be looking for, and we can find that by doing Newton's second law in the x direction. So we're going to make the left positive and the right negative, since we usually make the positive direction whichever way the acceleration is pointing. So we will have the net force in this case is just Fn. That's the only positive force, and there's no negative forces on this side. That's equal to mv squared over r to replace the centripetal acceleration. So we know the mass, we don't know the v, and we know the r. But the v we can find pretty easily because you have a couple formulas for v, which are v is equal to 2 pi r over t if you know the period, or 2 pi r f if you know the frequency. The frequency is the number of revolutions per second, which it says in this problem the frequency is 1 over pi revolutions per second, which seems like kind of an unusual number until you realize that whenever they give you things like that, they're usually trying to make your math easier, because if you plug the 1 over pi in for the f right here, the pi's will end up canceling out, and you just get v is equal to 2 times r, where the radius is 5, so the v, the speed of the riders, just ends up being a simple 10 meters per second. So we can take that and plug it in up here, which means that the normal force exerted on the woman is going to be her mass, which is 70, times the v, that's 10 squared, divided by the radius of the room, that's 5. So we have 70 times 10 squared, that's 7,000 divided by 5, which is equal to 1,400 newtons. So that's the amount of the normal force acting on the woman. In part C, it says state which force on the free body diagram prevents the woman from falling to the floor, or from falling when the floor is dropped down, and calculate the magnitude of that force. So the force that is preventing her from going in the downward direction is the upward frictional force. So we want to calculate the magnitude of the frictional force, and if you want to be specific about this, it is static friction. So the equation for static friction, if you remember the equation, was force of friction is mu s times Fn. But here's the problem that a lot of people are still having, is that you're forgetting that this is not actually the equation for static friction. This is the equation for the maximum static frictional force. So if we did the mu s of 0.6 times her normal force of 1400, which gives an answer of 840 newtons. That is not the actual frictional force acting on her. That is just the maximum possible frictional force that could happen in this situation. So remember, the way to do static frictional force is you have to set up a balanced forces with Newton's first law. Because with Newton's first law, in the y direction, net force in the y direction is equal to 0. That just means the upward forces is equal to the downward forces. So in this case, the frictional force is equal to the gravitational force. And since it's the frictional force that we're solving for, we don't even want to plug in a formula for this frictional force because we're looking for that. We just want to plug in the formula for the gravitational force, which is just m times g. So this is equal to mg, which is 70 times g is 10, which gives a frictional force, static frictional force of 700 newtons for part C. All right, part D. The paragraph response says the other three riders pictured all have significantly larger masses than the woman. So explain why these riders would not slide down the wall either, despite the fact that the calculations in both parts B and C are dependent on the mass of the rider. We saw in part B, it had a mass dependence, and in part C, it also had a mass dependence. So what this comes down to is that if let's just pick somebody and say they have a mass of twice as much. So if they have a mass of twice as much, that means that the frictional force acting on them, now I know this is supposed to be a written explanation, but I'm just showing the calculations for now so you can see how this works. Their frictional force, if this mass was twice as much, would be 1,400 newtons. Which, if you look at this compared to what we said up here, if the maximum frictional force is 840 newtons, this number, the 1,400 newtons, is bigger than that, which kind of implies the person would slide down the wall. But what you have to remember is that this number, the 840 newtons, depended on the normal force, and the normal force up here depended on the mass. So if the person's mass were doubled, they would actually have twice as much normal force. You can see this number right here would now turn into 2,800 newtons, which means that the maximum frictional force, when you do 0.6 times 2,800 newtons for the new normal force, you would get an answer that is double this number right here, which is 1,680 newtons. And now this number, the one we just calculated right here for the new frictional force, is still less than this number. So you can kind of explain this by saying that the normal force acting on the person would be higher, which means that the maximum static frictional force would be higher by the same factor, since it specifically depends on the normal force. And that also means that the person's actual frictional force, the true value of the frictional force, would also be twice as much for a person with twice the mass, let's say, which still gives you a number less than that maximum static frictional force. So no matter how much more the person weighed, no matter how many times larger they were with their mass, all these numbers would increase proportionally. So this number for the true value of the static frictional force could never be bigger than the maximum static frictional force.